I'm so mad at stuff for the last quiz because I was like, I'm not gonna get the conceptual right. And I got my brain, I was like, I wonder what I got wrong. But math.
Use the math stuff. Yeah. And then I think using your retake would be a good thing for to do now if you still have one. Because hopefully you can knock this one out of the park and go into the final. Yeah. I get that. The final is tricky, so I would, yeah, do the retake now for this one. Hopefully this exam goes a little bit better. It's really not too much, but anything retake related, I don't feel like I know because this is his first semester doing this. So like I don't know exactly how that works, but that sounds right. Okay, cool. All right, so yeah, electrochemistry, we talked about this for the first time on Friday. It's a little bit of a tricky thing to get down initially. But I think once you kind of understand the cathode to anode flow of things, it gets a lot better. So, right, we always see a bucket of water and another one, and they have these metal things called electrodes that are connected by a wire. And then we also learned that there's this thing right here connecting them. And what do we call this thing? Remember? This one has an inert salt on it. It's called the salt bridge.
Yeah.
So the salt bridge is basically to keep everything electrically neutral throughout, and I'll talk more about that a little bit later. But we have the site of oxidation, basically freeing up some electrons that can then travel over here to go to the site of reduction. So the site of oxidation, again, we talked about oxidation last unit. That's where we're losing electrons, right? Do you remember what the electrode is over here on this side? Anode. Yep. I think the best way to remember this is that um, anode and oxidation both start with a vowel. And then over here we have reduction. And this is called the cathode. And R and C are both consonants. So I think that's the simplest one. Also, sometimes people say an ox jumped over to the red cat. I don't know, whatever it takes. All you need to know is that this is where we are basically losing electrons and they're going over. We're becoming more positive in the solution. And we're basically then giving electrons over here so we can, the term is that they use is we can plate electrons onto this electrode. And when we do that, we're reducing this electrode. So that's a little bit of a concept review before we get into this stuff. But we also talked about, it's called a galvanic cell or a voltaic cell. Those things are used the same. There's another type of cell called electrolytic. He doesn't talk about that in this class. It could be on the final, but I don't think so. So really galvanic and voltaic is all you need to know. And the big thing to remember with galvanic cells is that their cell potential is always positive. So we're going to talk about that. I don't know if you really got into a lot of the math stuff on Friday. So what I'm going to talk about today might be a little bit of like a precursor to what you're doing tomorrow. But let's start basic. So we have a galvanic cell representing a redox reaction right here. Zinc going to form zinc 2 plus ions and copper 2 plus ions going to form copper solid. And I'm asking what would be the cathode's half reaction and what would be the anode's half reaction? Yes, cathode would be sorry, no. Cathode would be the copper. Yeah, yeah. So you got it. So since the copper 2 plus is going over to copper solid, that's going to be the site of we're getting less positive here, so that would be the site of reduction. So this is what's happening at the cathode, and then zinc going to zinc 2 plus is getting more positive, so we're losing electrons. That's going to be at the anode, the oxidation. So in other words, we could say that right here, this electrode is represented by zinc, and we're basically dumping out zinc 2 plus ions into the solution. And then over on this side, we could say that there's copper 2 plus ions that are being plated onto the electrode to form copper in its solid state. Hopefully you can see that pretty well. And then if we wanted to worry about balancing this, we would do something like this where we'd break into the two half reactions. So again, this part is kind of review of what you guys did last unit. how many electrons would we have to add to the product side here? 2, yep. And then over here, exactly, same thing. So these are already balanced, meaning we don't need to multiply by anything, so all good there. Say this was like a 3 and this was a 2, that's when we would have to multiply it to get the same coefficients, so we could cancel out the electrons, but we're already good. So now this is what might be new, because he didn't talk about voltage, did he? Okay. So when you're doing these redox reactions, all of these different reactions of like a metal going to form its ions has a standard reduction potential. So that is a value that we can attribute to this half reaction. And it's kind of talking about how strong of a reducing agent it is or how strong of an oxidizing agent it is. So I'll give a little bit more of an explanation about that in a second. But I'm asking what would the cell voltage be under standard conditions? And so I'll walk through this with you guys because we didn't talk about it. But the formula here is E cell. So that's what the cell voltage looks like. It's going to be with a capital E is equal to cathode minus anode. And you're always going to be given the standard potentials for these half reactions in a table that kind of looks like this. So if we're told that we have to do cathode minus anode, and here are the half reactions, then we were told the cathode has to be copper going to form copper solid, right? Because that's the site of reduction. If we look over here, we see that copper 2 plus going to form copper has a standard potential. Sometimes it says standard potential, sometimes it says standard reduction potential. Those are the same things. It has a standard potential of 0.34. So we're going to do the E cell is 0.34. This always has to be a minus here, minus the anode. And so the anode, we said, is going to be the zinc going to form zinc 2 plus. And so it's going to be written the opposite way as if it was being reduced. So zinc 2 plus going to form zinc is negative 0.76. So to be minus 0.76. So this is important because 76 is from right here. So when we're looking at this table, and I know it's kind of hard to see with like the colors and stuff, zinc 2 plus going to form zinc has a standard reduction potential of negative 0.76, meaning basically this is less good at being reduced than the copper, if that makes sense, since it's more negative. But we need to keep that negative in there when we do this formula, because something really important about galvanic cells or voltaic cells, because again, those are the same thing. Yep, exactly. This E cell, if it's ever a negative number, something went wrong. So we find that this ends up being 1.10, and the unit is volts. So it's always going to be volts. That's some physics thing talking about electricity. So that's kind of a good precursor. He'll talk more about this tomorrow. Now let's get back to the conceptual stuff. So in a galvanic cell, and again, that's the only type of cell we're going to talk about, electrons always flow from what to what? Yep, always from anode to cathode. So again, same deal up here where we're talking about electrons leaving this side and going over to this side. This one's a little bit trickier. Which electrode is losing mass throughout the process? As a hint, take a look at where the arrows are. One of them is an arrow going away from the electrode. One of them is an arrow going towards the electrode.
Oh, the electrode.
Yeah, the electrode specifically. Yeah, it's losing electron. Yeah, so we're going to say that the anode loses mass throughout this process because it's turning into these ions that are entering the solution. So instead of being solid zinc that's on the electrode, that zinc is then turning into an ion and entering the solution, losing mass. And from solid to aqueous. And then we could reverse that and say that over here at the cathode, the electrode's gaining mass because it's doing the opposite. We have aqueous ions that are being plated onto the electrode, creating more of the solid copper. Cool. Does that make sense? Awesome. All right, next thing. Salt bridge, I kind of talked about this earlier, is this thing in the middle. It has a inert solid. An inert solid, all that means is that it's not really reacting with anything. I don't know totally what that term means anyways, but I'm asking in the salt bridge, cations always travel towards what side and anions always travel towards what side? Cations travel towards the right, yes. So it's really easy to remember cations go to the cathode, anions go to the anode, and. That makes sense. To talk a little bit about why that's happening, though, we need to think again about what's going on in that solution. So if cations are going to the cathode, that's because we need to keep this electrically neutral. And basically, we're thinking about the solution. We said a second ago that we're basically putting these positive ions onto the electrode, we're plating them. And so in place of where those positive ions were, we need to add more positive ions to keep it neutral. Does that make sense? Basically, if we're losing positive things, we need to put more positive back in to keep it where it was. Yeah, cathode is getting more negative in the solution. Yep. And then anode is getting more positive in the solution, right? Because we're dumping out these positive ions into the solution. So to keep that balanced, we would need anions to go to that side. Okay. Next thing, this gets into one of not many equations that you need to memorize, or not memorize. This is on your formula sheet. This down here is something called the Nernst equation. E cell, non-standard. So you remember how last unit we used the like not symbol to represent standard things? This one looks like this. E cell equals E standard cell potential. And I should go back and clarify that this right here, this formula is specifically for standard cell potential. So the cathode minus anode formula is to find the standard cell potential. We can find a non-standard one, though, with the Nernst equation. So that's going to be equal to the standard cell potential minus 0.592, sorry, 0.0592 over N times the log of Q. And in this case, N is the number of electrons being transferred. So here I have same example with the zinc and copper, and I'm giving you some concentrations of the solution. So over on this side where we have the anode, we see that there's 0.01 molarity of the zinc 2+ ions. And over on the copper cathode side, it's 10 molarity. So that's what we're going to be using to find Q. So I'll kind of do this one with you guys because, again, new formula. Would it be what? So let me think for a sec. I think you're right. No, okay. So if we go back up to this equation up here, before we split it into the two half reactions, this is what we're using to find Q. And again, solids never go into Q. So it only would be the aqueous. So we can say that Q is equal to concentration of zinc 2+ over concentration of copper 2+. And that's it. Does that make sense? So I guess we could say that the cathode ions will always be in the reactant, so in the denominator. So again, if we have these concentrations given to us, don't worry about the SO4. That's like a counter ion in this case. Not too worried about that. All we need to know is that this is going to be 0.01 divided by 10. And I think that that is 0.001. Off the top of my head, that sounds right. And we're told that what the standard cell potential is. Again, we already found it ourselves, but they also give it to us in this problem. It's very possible he would ask you to find that yourself, and he would give you a table like this. And in that case, we would do the same thing of cathode minus anode, but we know that it's going to be E cell non-standard is equal to 1.10 minus 0.0592 over, what do we think N is? Again, if that's the number of electrons transferred. 2. 2, yep. We found it there. And again, if we had to do like some sort of multiplying here, like to balance it, maybe if I had to multiply this by 3 and this by 2 or whatever, it would be 6 or something like that. So it's always after you've balanced it. Times log of 0.001. So we would type that into our calculator, and I find that that ends up being E cell is equal to 1.19 volts. Is that okay? Cool. And then last thing I have for this one is I'm asking, do we think that this would be more spontaneous or less spontaneous than the standard cell potential? And this is something that it's kind of like you haven't learned that yet, so there's no reason to know. But basically, this value of E cell, the more positive it is, the more spontaneous it is. So this would be a little bit more spontaneous than the 1.10. Yeah, it's a little confusing. So yeah, delta G, we're always talking about negative is spontaneous, but for these, this standard reduction potential, the more positive it is, the more likely that's going to happen, pretty much. So in other words, up here, we could say that like F2 going to form 2F minus is super, super spontaneous because it has a standard reduction potential of 2.87. So yeah, that's all I got. You guys should be in a bit of